Hello students, welcome to EPG Pathshala. I am Rima Gupta from University of Delhi. So today we are going to discuss about the module Electrical and Magnetic Properties Part 2 from paper Ceramics. So students, let us see what we are going to learn in this module. So students, we will be learning about the relation of electrical mobility to diffusivity. Then we will be determining the temperature dependence of electrical conductivity and will be discussing about the conduction in ceramics. So before moving to the conduction, let us discuss what is electrical conductivity in ceramics. So the electrical conductivity in ceramics, as in most materials, is of two types. One is electronic and the another is ionic. So the electronic conduction is the passage of free electrons through a material, and in ceramics the ionic bonds holding the atoms together do not allow for free electrons. However, in some cases, the impurities of differing valence, that is, the possessing different number of bonding electron, may be included in the material, and these impurities may act as donors or acceptors of electrons. So in other cases, the transition metal or rare earth elements of varying valency may be included. So these impurity may act as centers of polarons or the species of electrons that create small region of local polarization, so as they move from atom to atom. So the electronically conductive ceramics are used as resistors, electrodes and heating elements. So if I talk about ionic conduction, the ionic conduction consists of a transit of ions, atoms of positive or negative charge from one side to another through point defects, and these are called vacancies in the crystal lattice. So at normal ambient temperatures, very little ion hopping takes place, and since the atoms are relatively low energy states, so the hopping is very less. Whereas at higher temperatures, however, the vacancies become mobile and certain ceramics exhibit what is known as fast ionic conduction occurs. So these ceramics are especially useful in gas sensors, fuel cells, batteries and so on. So students, let us discuss the electrical conduction in ceramics in detail now. So students, let us talk about analog to the electrical properties. So as you all know, the electrical force is given as Fi is equal to Zi into E into d phi by dx, which is equal to Zi E into capital E, where phi is the potential, E is the electric field, Zi is the atomic number, E is the electronic charge. So Zi into E is the total charge on the particle. So using the above relation, one can write the value of flux, that is Ji is equal to Ci Bi into Fi. So on substituting the value of force, we get Ji is equal to Ci into Zi into E into capital E times di by kt. So now since Ji is equal to Ci into Vi, so the velocity can be written as velocity, that is Vi, is equal to Zi di by kt into capital E, that is the electric field. Now defining the electrical mobility.
So electrical mobility is mu I, which is velocity per unit electric field. So mu I is equal to Vi divided by capital E. So on substituting the above equation, we get Zi E di by kt, and the units of mobility will be centimeter square per volts per seconds. Now comes the conduction in ceramics through metallic conductors. So while it is possible to apply Nernst-Einstein relation to express the motion of both ions and electrons to state similarity between electrons and ions, in reality the motion of electron is quite different. So in metals, the semiconductors at high mobility ceramics, the electrons and holes one considered as quasi-free particles with a drift velocity Vd, which is acquired under an applied electric field. The extent of this drift velocity is governed by various scattering phenomena such as scattering from the lattice. So under an applied field E, the force on an electron is given as F is equal to Z times E into capital E. In such conditions, the drift velocity increases in such a manner such that it is expressed by Newton's law of motion. So, the acceleration, that is m dv by dt plus mv by tau, that is damping, is equal to zee, which is force. So where m is the mass of the carrier, v is the velocity and tau is the relaxation time. So under steady state conditions, that is when carrier motion reaches a steady state, then dv by dt is equal to 0. Now comes the conduction in ceramics through metallic conductors. So while it is possible to apply Nernst-Einstein relation to express the motion of both ions and electrons to state similarity between electrons and ions, in reality the motion of electron is quite different. So in metals, the semiconductors at high mobility ceramics, the electrons and holes one considered as quasi-free particles with a drift velocity Vd, which is acquired under an applied electric field. The extent of this drift velocity is governed by various scattering phenomena such as scattering from the lattice. So under an applied field E, the force on an electron is given as F is equal to Z times E into capital E. In such conditions, the drift velocity increases in such a manner such that it is expressed by Newton's law of motion. So the acceleration, that is m dv by dt plus mv by tau, that is damping, is equal to zee, which is force. So where m is the mass of the carrier, v is the velocity and tau is the relaxation time. So under steady state conditions, that is when carrier motion reaches a steady state, then dv by dt is equal to 0.
Ionic conduction. So the conduction in the solid is often governed by the concentration of impurities, dopants and point defects. The conduction in these materials tend to be of polaronic or hopping type, which is migration of charges between either two dissimilar charged ions or counter migration of ions and defects such as vacancies. So in ionic solids, The proximity of carriers to the ions result in the formation of polarized region, that is a polaron, which may be longer or smaller than size of the unit cell. The effective mass can be taken as to that of a free electron, that is Me star is equal to Me star free electron. So large polarons, ions, and hence electronic mobility expression can be valid for a polarons. So, in a number of ionic systems such as lithium niobate, that is LiNbO3, cobalt ferrite, that is COFe2O4, and FeO, etc., carrier ion interaction is strong, and hence these are called strongly correlated systems. So, in such cases, a polaron are smaller sizes and effectively mass bind to be a larger that of a free electron. So in such systems, motion of carriers is thermally activated, that is through hopping mechanism. So the conduction in such cases is determined by the dopant concentration, and hence higher the dopant concentration, higher the conductivity, and this concentration that is higher is within the appropriate limit. So in contrast, in band model, carrier concentration is determined by the temperature. In ionic solids, while carrier concentration is independent of temperature, that is within the extrinsic region, the mobility is strongly affected by the temperature and is expressed as mu is directly proportional to exponential minus EA by kT, where this EA is the activation or migration energy, T is the temperature, and K is the constant.
Before moving to total conductivity, the ionic and electronic conductivity. So the electrical conductivity of a species, let us say I, so the sigma I, that is electrical conductivity, is defined as a charge flux per unit electric field. So the units are ohm, centimeter, both inverse, or we can say Siemens per meter. So the electrical conductivity sigma I is given as Q by T divided by A. So the expression comes out to be Ci Zi E Vi upon capital E. So sigma I is equal to Ci Zi E into mu I, where Ji is the flux of the ith species. So for ionic species, we can apply Nernst-Einstein equation such that the sigma I becomes Ci Zi square E square Di by kT. Note that as we saw earlier that the temperature dependence of diffusivity shows two distinct regions, a low temperature extrinsic region and a high temperature intrinsic region. For the same reasons, the temperature dependence of ionic conductivity also exhibit intrinsic and extrinsic regions. While in intrinsic regions, the conductivity is governed only by defect migration, as defect concentration is independent of temperature in the extrinsic region. So in this case, the defect concentration is temperature dependent as well as leading to higher slopes of the log sigma versus 1 by T plot. Now, if we talk about the total conductivity, can be given as, since all charged species contribute to the electrical conductivity, we can write the total conductivity as sigma, which is equal to sigma 1 plus sigma 2 up to sigma I. So this total conductivity is consist of ionic and electronic conductivity, where electronic conductivity is sigma E is equal to NE mu E plus NH mu H. Now the total conductivity will be the sum of all conductivities. The fraction of total conductivity carried by each charged species is called transference number, that is Ti, and is expressed as Ti is equal to sigma I divided by sigma, and it is straightforward to see that T1 plus T2 and up to Ti is equal to 1. So naturally, when for a predominantly electronic conductor, the T is approximately T electronic, which is 1, and for ionic conductor T is T ionic, approximately 1, whereas for mixed conduction it is T electronic is equal to T ionic.
Characteristics of ionic conduction. So, the long range migration of ionic charge carriers through the lattice under application of an electric field, for example, migration of Na plus ion in soda silicate glass. They are dependent on the presence of the vacant sites in the neighborhood of the mobile defects or ions. They can occur through the grain boundaries, such as in polycrystalline ceramics, or through the lattice, as in fast ion conductors. But when the electric field is absent, the thermal energy, that is kT, is required for counter migration of ions and vacancies, overcoming the migration energy, that is EA.
So students, you can see on the right hand side, which shows the schematic showing the lattice ions and vacancies in a potential well with and without applied electric field. So here EA correspond to the migration energy. So in presence of electric field, the potential energy is tilted to one side, leading to higher driving force for migration towards one side than to another side. The field is small enough not to pull the ions out, rather it is enough to tilt the energy level such that ions move in one direction preferentially. So the ionic conductivity is prompted by the small ionic size, small charge, that is less Coulomb interaction between ions, favorable lattice geometry, and so on. Theory of ionic conduction. So now consider one-dimensional movement of ions in a lattice as shown schematically in this figure. So the distance between two ionic sites is delta, and in the absence of any field, the ions required to overcome an energy barrier of strength EA or the activation energy. So in the absence of any field, the probability of ion moving to its left or right according to Boltzmann's statistics is equal and given as P is equal to 1 by 2 alpha V exponential minus EA by KT. So where alpha is the accommodation coefficient related to the irreversibility of the jump, V is the vibrational frequency of the ions, EA can be considered as activation energy or free energy change per unit atom. So now when the field E is applied, let's see what will happen. Now when the field E is applied and if the ionic charge is Z, then the force experienced by the ion would be ZE into capital E. So as a result of application of this force, the energy levels on the left and right of the ion would move up and down by a magnitude of half F into delta or half ZE delta E, with the total energy change being ZEE into delta. Now, the probability that ions will move to its right is given as P is equal to alpha V by 2 exponential minus EA minus 1 by 2 ZEE delta by KT, which is equal to P exponential ZEE delta by 2KT. Similarly, the probability of ions moving to its left would be P is equal to 1 by 2 exponential minus EA plus 1 by 2 ZEE delta by KT. So the above expression shows that at any given temperature, the probability of the ion moving to right is higher than to the left. That is, capital P for the right is greater than capital P for the left. This results in net motion of ions towards the right, that is, along the direction of the field, and as a consequence they acquire an average drift velocity, that is V average. So this velocity is given as V average is equal to delta into P right minus P left. So on substituting the values from the above expression, we get that 1 by 2 delta P into exponential ZEE delta by 2KT minus exponential minus ZEE delta by 2KT. So invoking a relation equivalent to sine hyperbolic, we get that V average is equal to delta P sine hyperbolic into ZEE delta by 2KT. So now under normal circumstances and normal field for ceramic conduction, the fields are quite small and a few volts per centimeter, and thus the field induced energy change is small as compared to thermal energy. That is, 1 by 2 ZEE delta is very less than KT. So this modifies our equation and the equation becomes V average is approximately equal to ZE delta square PE by 2KT. However, if 1 by 2 ZEE delta is much greater than KT, then V average is approximately equal to A times exponential ZEE by 2KT. Now, at low field strength, assuming the validity of Ohm's law, at low field strengths, assuming the validity of Ohm's law, we write the current density, that is J is equal to NEZ into V average, where N is the ionic density per cc and total charge is Ze. Hence, Z is equal to NZE delta square PZEE by 2KT, which is equal to Ne square delta square Z square PE by 2KT. Now we know that P is equal to alpha nu exponential minus EA by KT. So, J becomes N alpha nu E square delta square Z square upon 2KT times exponential minus EA by KT into E. Since J is equal to alpha E, one can find the expression of sigma which is given in this slide. So this expression has similar form that we worked out using diffusibility and mobility earlier, and again show the similar dependence on temperature as well as activation energy for migration.
Conduction in ceramics. The conductivity of many beta prime and beta double prime alumina are very high and vary between 10 to 10 to power minus 1 per ohm per centimeter over a temperature range of 300 Kelvin to 675 Kelvin, and these also have typical activation energies between 3.5 to between 3.5 to 4.5 kilocalorie per mole. The spinel oxides such as Fe3O4 have conductivities of the order 0.5 per ohm per centimeter and have very low activation energies, typically about 0.35 kilocalorie per mole, representing almost temperature independent behavior. So the compounds like Y2O3, that is yttrium oxide, next is hafnium oxide, that is HFO2, silicon dioxide SiO2, aluminium oxide, that is Al2O3, are far more insulating and have conductivities in the range of 10 to power minus 5 to 10 to power minus 14 per ohm per centimeter in the temperature range 400 to 1000 kelvins. So students, let us summarize what we have learned in this module. So students, we have first discussed about the ionic conductivity. The ionic conductivity has an Arrhenius-like behavior and is governed by the concentration of migrating species, temperatures and activation energy. Since many materials will have both electronic and ionic conduction and hence a term transference number, that is T, was defined, and which is the sum of electronic and ionic contributions to electrical conduction. For ionic ceramics in applications such as fuel cells, one require Ti to be as high as possible. So the fast ion conductors have open structures resulting in lower migration energy for defect diffusion, permitting fast transport of ions such as in beta prime and beta double prime alumina, resulting in sustainability, that is highly electrical conductivity of the order of 10 to 10 to power minus 1 per ohm per centimeter over a temperature range of 300 to 675 Kelvin. Thank you.